Hello everyone, this is Greg Ristabin from Olympus. I'd like to welcome you today to this webinar entitled Best Practices to Increase Production and QC PMI for Tube, Pipe, Rod and Wire Manufacturing. This webinar will demonstrate how to achieve 100% grade chemistry QC. Our presenter today is Ken Smith. Ken is the Global Business Development Manager for Olympus and has been working with portable and automated analyzers for over 25 years. This webinar will last approximately a half an hour to 45 minutes. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the course of the presentation. The chat panel will not be monitored for Q&A during the presentation. If we aren't able to get to your question during the live webinar, they will be addressed either personally by email or phone after the event. Now, without further ado, I would like to turn the presentation over to Ken Smith. Ken, take it away.
Thank you, Greg. My name is Ken Smith, and I want to welcome you and thank you for joining today's discussion. If you thought that Olympus makes cameras, you're right. Olympus does make cameras, and they make a wide range of optical technologies for research, medical, and industrial testing. We'll spend about 5 minutes or so giving you a little background on Olympus Scientific Solutions Americas. The balance of the time will be spent discussing how XRF analysis can be applied as a quality control step for the manufacture of alloy-based materials. Can I go? Olympus has been in the optical technology business for nearly 100 years. We continue to innovate products and technologies that expand the boundaries of digital photography and audio capture. Olympus's optical technology provides tools supporting less invasive procedures, innovative diagnostic and therapeutic endoscopy, and early-stage cancer evaluation and treatments. But today's discussion focuses within the industrial segment of Olympus's technologies. As you look at the industries identified by this slide, such as aerospace, power generation, oil, gas, petroleum production, it is clear that the ability to make a direct, non-destructive measurement of alloy grade and chemistry is a common requirement. Advanced NDT Solutions describes how Olympus uses an array technique to extend the typical range of NDT technologies. This approach combines instruments, probes, software, and scanners to speed and streamline a more complete application solution. As a manufacturer of a comprehensive range of handheld non-destructive testing methods, the step to automated online systems is a natural progression. Eddy current technologies test for surface flaws, ultrasonic testing identifies internal flaws, and XRF testing provides compositional analysis in terms of elemental chemistry and alloy grade identification. In 2010, Olympus added analytical X-ray technologies to their family of non-destructive testing methods by purchasing Innovex systems and in situ technologies. In situ manufactured an innovative X-ray diffraction system for doing crystalline-based compositional analysis. The small size and rapid throughput of this technology makes it valuable for mineralogy and corrosion analysis using dry powder samples. On the other hand, X-ray fluorescence is most commonly used as a handheld device for alloy analysis. And it is a success with direct reading field instrumentation that brought many customers to us asking for a way to use XRF in a fully automated manufacturing process. This slide refers to online conveyor belt-based X-ray sorting systems that allow the processing of 15 to 150 tons per hour of material. Pulling copper out of ferrous shred streams and identifying and removing lead and other undesirable materials from glass recycling streams are the most common automated conveyor belt applications. While there are a range of form factors, In most cases, systems can be battery operated and fully field portable. So the FOX-IQ system is part of this broad family of non-destructive industrial testing technologies. While we also offer an online process liquid XRF analyzer, today's discussion focuses on the FOX-IQ system for QC testing of tube, rod, and wire forms of alloy materials. Tens of thousands of handheld XRF analyzers are in use today, providing simple point-and-shoot grade ID and alloy chemistry. XRF for alloy PMI and QC is broadly accepted and applied as a technology. The slide shows the analytical performance based on a 3-second analysis. The titanium, which separates stainless 321 from grades 304 or 303, is accurately measured. While this test happened to hit the exact amount of titanium, the precision of the measurement is plus or minus 0.05%. Looking at the chrome level in the same test, we can see that the reading is very accurate as well. The picture on the left is the CERT chemistry, and you can see that the actual amount of chrome is 17.15, and then the analysis, which is on the left, is showing chrome at 17.12. So you can see we're hitting the numbers pretty much spot on. So now I want to take a minute to talk about how XRF is able to provide these real-time quantitative values. Using an X-ray tube, we start by creating and directing an X-ray beam into the sample material. The lighting up of the sample occurs when the X-ray energy temporarily knocks an electron out of its orbital, ionizing an atom. In the process of transitioning from a positive ion back to electrically neutral, the lit up sample emits an X-ray energy that is specific for each element. The detector captures the spectrum of energy as displayed here, and beyond calculating the chemistry from the spectrum, the elemental values can be used to determine the grade match. What's happening in the algorithm basically is we're correcting for background and interferences from other elements. Once we get a net signal for each element, we're able to apply our calibration algorithm and determine the percent concentration. This process, as far as the user is concerned, is really real time. The test starts and the answer is directly displayed. The emitted energy in real time is turned into a elemental analysis, as you can see on the right of the slide. The algorithms are different from application to application, but all of them turn in a quantitative result. While the slide diagrams that we've been looking at show single atoms, in reality, tens of thousands of signature X-rays are captured by the detector every second. As long as the sample's surface is representative of the entire sample, fast, accurate, and quantitative results can be achieved in just a few seconds. This slide is meant to bring your attention to the fact that field X-ray analysis for analytical purposes is a near surface test. In the diagram, we have something that is meant to be the thickness of a human hair. We call it a piece of stainless steel that's 70 microns in diameter. If analyzing that with the FOX-IQ system, the depth of penetration would be only 10 microns. So the reading depends on the surface being representative of the entire sample. Because XRF is a near surface measurement, grinding or cleaning is required to remove coatings, plating, scale, oxide layer, metal dust. The surface must be representative of the whole. Shot blasting is often a way of treating low alloy steels to keep them from rusting while they're being delivered, or sandblasting can be applied as well to condition the surface and make it look in a desirable way. These things all can cause problems for XRF and can require that the surface be conditioned. But what's important for this discussion today is the vast majority of our nearly 100 installations, systematic surface prep is rarely required. Typically the testing is done toward the end, the finishing end of the process where the sample is clean, sufficiently clean. So the surface measurement surface condition is important, but typically we're able to test it at a point in the process where that's not an issue. Our stated elemental limits run from phosphorus to plutonium. Typically based on customer needs, analyzers are set up to measure from titanium to bismuth. By the end of the calendar year, the elemental range will be extended to aluminum as an alloying material in iron, copper, nickel, or titanium grades. Typical applications, I've built a little chart here. We have mostly the tube, rod, and wire installations. However, there are coatings and thin sample customers. Mainly the thin sample customers are precious metals coatings and solar panels, surface coatings for brake discs, and material composition for filter paper. Metals testing for mining samples is also a common interest, but in any case, the great majority are tube, rod, and wire installations. If a picture is worth 1,000 words, I believe a brief video of a system in operation will help you to understand exactly what we're talking about. So I'm going to take a minute here and share my screen so I can show you a video. Okay, here we go. I'm freezing it there to show you this is the controller, and it can be used to manually initiate a test, which is what's happening right now. Typically, the test is automated, and the programmable controller that's running the process is telling the system to test now. It shows that it's busy, and you can see there that a new rod has been moved into position over the probe head. Run it a little further. After that, you're going to see the test status reported in a second. It shows busy and then pass on the controller. That would also be sending a signal to the process control system to move the rod along. So the new rod comes forward into position, and then the manufacturing process there moves the material off to the end of the line. Okay. All right. Now that you've heard the basics about XRF technology and have seen a Fox IQ in operation, we can be a bit more specific about how alloy tube, rod, and wire manufacturers think about whether automated online XRF can contribute to the quality and productivity of their process. There we go. All right. First things first, how much does it cost? That's what that's where the thinking starts. What's the return on the investment? In terms of how to think through ROI, of course it depends to some extent on the operation itself about how they would want to think about it, but I've created a table here to sort of cover the basic assumptions. The first and most critical things to think about is the volume of material that's being handled and the length of time for each test. I've shown single, double, and 24/7 operations. I'm assuming that the lines would be running 85% of the time. That's just a number that I pulled out of the air. It seems reasonable. Every process has its starts and stops and interruptions. The instrument can run 24/7 without being interrupted, but manufacturing processes have interruptions. The tests per minute, I've picked 6. That would be a test every 10 seconds. In reality, that's a pretty typical cycle time. The cycle time is not just the time to analyze the sample, and you also have to add in the handshaking time between the analyzer and the control system, and you have to add in the movement of the sample to the analyzer and away from it. So all of those things go into the cycle time. We have some tests that are running in a 5-second cycle. In some places, the material isn't moving that fast, and it might sit for 30 seconds. 10 samples a minute is a pretty typical cycle time. I show the system cost with installation. There's an additional fee for traveling out and spending a couple of days to commission the system that's included in a ballpark way in that number. Then I show the number of tests for 3 years based on the volume. And in the end, the maintenance cost is in there, which is really about the X-ray tube needing to be replaced about every 3 years for a single shift operation. So when you put all of this together, these assumptions, the cost per test is between 1 and 5 cents. So once people have thought about that, there's still more to think through. One of the places to start is, will a Fox IQ work for your application? And I've divided my answer to this into probably yes or maybe no. If you're currently using a handheld XRF to sort your alloys, probably, and I would say, 99 out of 100 times, we're going to be able to do it with the Fox IQ. Running high alloy steels, meaning that the iron content is 95% or less, and the alloying materials are 5% or more. This would be stainless steels, chrome moly steels, tool steels. Running copper, nickel, titanium, cobalt, tungsten, zirconium alloys, those are commonly straightforward applications for us. So I would expect to be able to do these applications, although we would want to talk about it and make sure that we weren't overlooking any details. The Fox IQ might not be able to meet your application needs if you're running low alloy steels. We have customers that are running low alloy steels, but we need to look at your list and think through your analytical goals, because it's harder to separate low alloy steels, and the ability to measure carbon is not something that X-ray is able to do. Running aluminum alloys, we have customers that are using the system for aluminum alloys, but again, we can't do everything that might want to be done with an aluminum alloy, so that would be something we'd have to look at closely. And magnesium alloys are similar. Sorting your grades depends on low levels, less than 1% of aluminum, silicon, sulfur, or phosphorus. We would want to look carefully at that application. We might not be able to do it. If we've gotten this far through it and it's still looking like a good idea for the operation, we usually give them an application statement that they work through to help us to understand and define the application. Want to know what they're trying to do, how they're making quality and control measurements currently, what their goals are in implementing this process. And we start talking about how the sample is going to be delivered to the window, and what the size, shape is, what the cycle time requirements are. And then there's a few more things to think through. Again, we've talked about analytical goals in a little more detail. There are installations where the manufacturer is satisfied that they have 3 or 4 or 5 or 6 different materials, and all they really need to do is to be sure that they're not mixing that finite universe of alloys. Some people want to make sure that all the required elements in the grade are within the spec. Some people want a detailed material chemistry for their quality records and to pass on to their customers. Other people are interested in keeping track of key elements. You know, they want tramp elements to get out of range or to make sure that they have enough of what they're looking for. The site details, we need to get pretty detailed at some point to understand the challenges of the installation. And then in the end, we have to start talking about, once we've made the measurement, how are we going to communicate with your controller, and what sort of an output are you going to want. I'm going to try to bring up my laser pointer. Let me see if I can do that. No, sorry. There, I've got it. Okay. The controller is at the center of the Fox IQ installation, and it's in the center of this slide. While we provide detailed guidance for installation, the physical installation of the system is the customer's responsibility. Every system has a controller, a probe head, which is down there, a PC for the setup and manual operation of the system, and also for handling data storage and exporting. These components are connected via industrial cables, maximum distance of length of 30 meters. Of course, we're going to be connecting to your PLC. Once we start communicating, we have two different options for communicating. The level one is the analog level. This is from the client's, the customer's PLC to the Fox IQ control box. We use dry contacts with a 24-volt signal from the PLC. And we're controlling just very basic signals. Start a test, safety interlock so that the controller for the plant can shut down our X-ray tube if it wants to. Output, pass, fail. We tell the PLC that we're busy when we're running a test, and we tell, for safety purposes, the PLC that the X-ray tube is active. Second kind of control communication is digital. The digital allows the same exact sorts of control options as the analog channels would. Also, we've got a broader and more capable ability to communicate. We can give you element by element concentrations, the X-ray spectrum if you want that sent off, the analyzer hardware status. Some people want to know how the system's doing and track that over time. Between the PLC process computer and the Fox IQ PC software, we have something called an application program interface, an API. And this is a software utility that basically allows your PLC to query and control our PC software directly. There's a host part to that and a client part to that reside on the PC. The Fox IQ can be used basically anywhere that a handheld system could be used. The key is to be able to deliver the sample in a precise and repeatable way to the probe head. It's easy to see in this case with a wire sample that you've got to pay attention and get the sample over the window. Whether large or small, the samples must be reliably delivered to the window on the probe head. The sample needs to be centered and as close to the window as possible. If not in contact, then within a few millimeters. And then final details that people need to work through with our engineers and sales staff. We need a definitive alloy grade list. We have to know everything that's going to be tested. We need to take time to define the analytical goals so everybody understands what we're aiming to do. And from those discussions, we developed something called a final acceptance criteria that defines what the system will do and how well it will do it. That done, we usually get customer samples and run them through and develop statistics and give them the data to prove the performance of the system. Once a system is being brought into operation, there are two different options for doing alloy grade identification. The first is the fingerprint method, and it's a simple comparison to a spectral fingerprint from a suitable reference material. You want to run a 316 test, you shoot a 316 sample, make that your point of comparison and compare the other components that are running through that are that grade against that. The second type of grade ID is a grade specification where we not only capture the spectral fingerprint, but we calculate the chemistry for the sample and compare that chemistry to the grade spec. In either case, both methods are included as standard. When you get a FoxIQ system, it can run either way. Both methods also use a site-specific reference library for grade matching. We have a factory library that has 500 grades, but most people are going to be adding custom grades or changing names or doing something. Typically, it's a custom library in the end. When you're looking at grade specification, I like to describe it as having three different kinds of elements in a grade. There are required elements, and these are by far the most important part of sorting and identifying materials. And basically a required element is any element that has to be in the alloy in order to make it. So it's something where the minimum value is greater than 0. Tolerated elements, on the other hand, can be named in the grade spec, but the minimum amount is 0. So you don't have to have, for example, manganese in a stainless steel to meet the grade spec. However, there is a maximum amount, so there's a most or a max limit that can be tolerated. Typically, this tolerated elements don't make up very much of the alloy, and they don't help very much in sorting versus other grades. The last type of element that I'll mention is an unspecified element or a tramp element, and virtually every kind of alloy has tramp elements in it, and our library gives you the ability to define to what level you would be willing to allow a tramp material to exist. So common things like tungsten and cobalt and vanadium, which show up in stainless steels, you can put a max value in there and not let the fact that they're floating around at 0.07% create any sort of interference with grade identification. Wanted to take a minute here to just kind of go through the FoxIQ tube and rod operating system. I'm not going to get into a lot of detail, but I'm going to just go through how things are set up and operate to give you an idea of the functionality and the simplicity of this system. It's a nice batch-based manufacturing system. The setup screen allows the user to create a type-based reference library made of spectral fingerprints. In this case, I've circled where the fingerprints are placed. We have a few different 316 fingerprints and a pure iron fingerprint in there just by chance. There's also 2 levels to this match criteria. Not only do we look at the spectrum, but we also can look at an isolated region grade by grade to look at a specific element. And this technique of looking at the whole spectrum and one specific special element within it improves the speed and analytical confidence of the system considerably. Helps a lot with grades that are very similar. The setup screen here, I'm just focusing on another region inside the red oval where settings can be optimized. This is a simple process where by you shoot each sample of the kinds that you expect to handle, and you determine your cutoff settings, what's going to pass and what's going to fail, based on the readings that you get as you go through the universe of materials that you're going to test. For this reason, the spectral matching is typically used in a place where the universe of alloys is less than 12 grades, because the comparison of all the different ways turns into pretty long process. However, it's not something that can't be done. So it could be more than 12. I'm just saying typically it's not chosen. Inside the rectangular region, we're looking at where selections are made about what to do if a sample fails. And some systems automatically move it into a reject bin. Some places a person has to come by to take it away. And there's also the ability to set up a set number of retests before you fail a system. The batch test screen is where a production run is given a name and an alloy grade / fingerprint is selected from the alloy grade library to run the test. You can interrupt the test if you have to stop for some reason and then continue it. The measure screen shows the status of an individual test as well, as the progress through the batch, and it would count the fails if there were any fails, and it's showing that the X-ray tube is on. The next screen is showing what a fail looks like, and in this case we've set it up to give us a suggested match. So not only does it know that it isn't 316 stainless steel, it's telling us that it should be 347. Here you can see our progress. We've got a pass count of 4 and a fail count of 2. When the run is complete, the results screen presents a summary and provides 2 options for generating a report. The export option results in a .csv file that is basically a spreadsheet. So just to summarize the topics that we've covered here and wrap things up, the starting point is that the analytical requirements are defined and acceptance required is developed, and it's demonstrated that it can be met. The site-specific installation details have to be understood and incorporated in the plan to move forward. Installation and commissioning, typically, as I've mentioned, it's a 2-day training and startup assistance is required. There's a charge for this. It's a few $1,000s, and it's more or less depending on how far it is from where our field service engineers are going to be embarking on their travel. The other thing that happens with the installation is the field service engineers work through the details of the installation and the process control integration. They support the local people as they're making these decisions and implementing the installation. After sales support, product has a 1-year factory warranty. Some customers choose to purchase an extended warranty. Troubleshooting options, first is of course phone support. Second option is a remote access to the system via the internet. We are able to get around a lot of the issues that customers have with a remote session. The third option, say that your X-ray tube were to fail, is to have a loaner probe head sent to you to swap out while the repair is being made, the replacement X-ray tube. Some companies, particularly companies that have multiple systems, will actually buy a spare probe head and rotate it through like a spare tire so that they're always ready to just take 15 minutes to swap out if that were to happen and keep going. The fourth option is a site visit by one of our field service engineers. So thank you very much for your joining us and your attention. If you're interested in further information, you can contact us, and we will be directly addressing any questions that you've sent us. I have a few questions that have been passed to me that have come in, and I'd like to just take a minute to go through those quickly because I think the ones that have been passed up apply in general to people. One of the questions that came in is the radiation level dangerous? There's no amount of radiation that is good for anybody or recommended. It is regulated, and all the installations use shielding in some manner depending on their layout and their state requirements. Sometimes there's a metal or a leaded Lexan enclosure that's put around the probe head, just a small enclosure. Sometimes all that needs to be done is that the area has to be set up so that people can't get near the system. But it is an open beam system, and the radiation has to be managed, and we provide guidance for that. It's a routine thing. Somebody wondered if there were some customer examples of where people are using our system. When was the first system installed? The first system, I think, was installed in 2008. It was one of several that we've installed with Sandvik. I'm not meaning to imply that they're endorsing or not endorsing our product, but the question coming up here. And typically manufacturers of stainless steel tubing are common customers, people like Plymouth Tube or Salem Tube or even Carpenter Technology range of companies. So you've certainly heard of the companies if you're in that business that are using our equipment. The last question I want to address is somebody asked how sensitive is the system to sample size, shape, positioning. And the system is pretty hardy with regard to size and shape of the sample. We can do from a small wire to all kinds of shapes, but the key thing is you've got to get the sample over the window and as close as possible. And it's fairly forgiving with big samples, but in general, the better the delivery of the sample to the window, the more repeatable and precise, the less there can be difficulty with the system. So that's pretty much everything that I have to cover today. And again, thank you for joining us.
Thank you, Ken. On behalf of Olympus, I'd like to thank all the attendees for joining us, and Ken for his expertise and participation in today's event. We hope this material was informative and useful. This webinar, along with the Q&A, will be archived on our website at www.olympus-ims.com. Everyone who registered for the event will receive a follow-up email with links to the archived presentation. That's going to do it for today. Thanks again for participating, and we'll see you all again next time.